Hello and welcome to another LeetCode problem. So today we're going to be doing problem number 1376, time needed to inform all employees. And so this explanation is a little bit confusing, but let's go over it. The company has n employees with a unique ID for each employee 0 to n minus 1. The head of the company is the one with the head ID. Each employee has one direct manager given in the manager array, where manager I is the direct manager of the ith employee, and manager head ID equals -1. Also, it's guaranteed that the subordination relationships have a tree structure. The head of the company wants to inform all company employees of an urgent piece of news. He will inform his direct subordinates, they will inform their subordinates, and so on until the employees know the urgent news. The ith employee needs inform time I, minutes, to inform all of his direct subordinates. Return the number of minutes needed to inform the employees about the urgent news. And so this first example, we only have a head, and so he doesn't need to inform anyone, so that's 0. But in the second example, if we have an employer with a bunch of subordinates, just 1, 3, 4, 5. So as you can see, the inform time for employer number 2 is 1 second. So for every single child of his, it takes 1 second to inform the children, and so it takes 1 second to inform them all. So the total inform time here would be 1. But so this is a pretty easy question, but let's just look at how this would be a little bit more complicated if we had some more stuff, right? So 3, 4. Let's just say something like this. Let's say maybe 5, 6. Let's say like this. So how would we do something like this? Well, it's pretty straightforward, right? We can simply know that here the inform time is at 0. Then when we go to the children, we would add whatever inform time it takes for this person to inform his employees. So let's just say that's, I don't know, like a second maybe. Then we'll add here the amount of time that this guy takes to inform his employees. Let's say whatever that is, 2. And then maybe this is 1 again. And so how do we figure out the time it takes to inform all employees? So this can be changed to not the time it takes to inform all employees, but the time it takes to inform the last employee, right? So the longest time it takes to inform someone is going to be the time it takes to inform all employees. And so simply what we have to do is we just have to go down these nodes, and we just have to get, once we get to a leaf node, we can say, okay, what time are we at? And is that time greater than our last max time? And if it is, we just change it. So like here, we can have a node, and then we can have some time that we're at, right? So we'd have node 2 with time 0, we'd have node 3 with time 1, we'd have node 6 with time 3 altogether, and we'd have node 7 with time 4. And then I think this would be the answer. And so that's how we would do it. We would go down the nodes, and we can just keep adding the time it takes to inform the next employee. And then we can just keep checking, are we at a bigger result than we had before? And we're just going to keep doing that. And then that way we're going to be guaranteed to get the max output. Now, another tricky part about this problem is we're not actually given this tree, right? We're just given some stuff. So how do we make a tree? Well, what represents an edge? So an edge actually represents an edge between the manager and its employee, right? And so we have this managers array. So we can simply go through this managers array, and the value is the manager, and then the index is the person he manages, right? So like in this array, well, let's think what this array would look like for this tree, right? So let's do that. So so there are how many nodes here, by the way? So this technically would also be, let's just say there's a 1 here, maybe like this, right? And let's draw this array and what it would look like for this tree, and then we can easily figure out how to get the edges. So let's just say now we do have 1 through 7. And so we can see that, remember, the manager is the number. And so for 1, the manager is 4. So it would be 4. For 2, the manager is no one, so -1. For 3, the manager is 2. For 4, the manager is 2. For 5, the manager is 3. And then for 6, the manager is 3. For 7, the manager is 6. And so that's what the array would look like, where these values are the manager, and then the index is the node they manage. So we can simply have a dictionary, right? So we can just have something called like paths, where the key is the manager. So for example, let's say the manager would be 2 here. And then we would go through all these. We can just enumerate through this. And we can say for every single node, we take the value, which is going to be the key, and then the index is going to be added to the people that he manages. So in this case, for paths 2, who would he manage? He would manage 3 and he would manage 4. But this doesn't have to be a binary tree. It can be as many trees. It can be as much as you want. Then we simply just start at the head node, which we're given, and we can just move down to all the children. So we'll just say, like, for every single child in this, go down to them, get the values, and we don't have to keep any track of visited, because this is going to be like a directed graph. So we're only gonna store the nodes that go from manager to, like this, from manager to person they manage, not the other way around. So we'll just simply have to go down paths, keep going down paths until we run out of stuff to go down, right? So for example, let's say we go to 3. Well, what does 3 manage? So 3 would manage 5 and 6. And so we'd go down to 5 and 6. 5 doesn't manage anything, so we'd be done. And then 6 manages 7. So we'd go down to 7, and so on. And then so we'd go down to every single value. We would update the total time it takes to inform the person using our inform time array. And then we just get the maximum there by just every time we get to a node. Honestly, we don't even have to do that. We can just, I mean, it wouldn't really change the complexity. What we could do is we could get to a node and we only have to check nodes that are actually a leaf node, right? Because any non-leaf node is definitely not going to be the longest inform time, but it doesn't matter. We can do one, so we can do that. Okay, anyway. So let's just do, yeah, so we can do only leaf nodes. So let's first of all do a couple things, right? Let's make this path dictionary. So paths equals default dict list. Now let's do for I, v, and enumerate. And then we're going to be enumerating the manager. And then remember paths value, right? Oh, so we do need to do check one more thing. So if value does not equal -1, right? Because if it's -1, then you're your own manager and we don't want a path there. So paths value dot append, and then this is going to be I. Okay, so now that we have our tree, we need a result. So let's just say that's 0. Now let's have a DFS. So this is just going to be a normal def first search of a tree. So def DFS. We're going to have a node and we're going to have a time. And then we can simply do if node not in paths, meaning there are no paths from this node, then we can figure out what's the biggest value, our result or our current result. So we can just throw in non-local here res, and then res equals max res time. Okay. Now otherwise, and we can actually just have an else, because if there are no paths, we're just done. So we can just return. Now else, what we need to do is we need to say, we need to visit every single child of the current node we're at, right? So for, let's just say child in paths node. So for every single child that this node is connected to, we need to visit that child. So we just need to say DFS child. Now we need to have time plus the additional time it takes to inform its employee, right? So if we're at this node, when we go to this node, we need to have whatever time we have here plus the time it takes to inform the employee. And that would be just inform time at the index we're currently at. So that's going to be inform time, whatever index we're at, would just be node. Okay, so we would go down there and we would do this kind of thing again. And I think that's actually all the code for the DFS. So now we simply call DFS on, so remember we need to call the DFS on the head ID. And our initial time is time 0. Then we just return res here. Let's try that. We have if I'm doing value. Okay, this is v. Done a lot of coding today, so my brain's kind of fried. Okay, so So that's, as you can see, it's pretty straightforward. Once you've learned that how to connect these nodes and how to traverse down, it's pretty straightforward. The inform time is just a basic DFS. And we just literally take every child node, take every leaf node, and we just get a maximum there. Now there is another way to do it, I think. You can technically probably return like the max child value. So instead of having this res, you can probably, instead of passing in this time, you can probably just return the max child. And you can code it up that way if you like, but this is going to be the same time complexity and it's just a little bit more straightforward. So anyway, so let's think of the time and space complexity for this problem. So for the time, we're visiting every node maximum one time, right? Because it's a directed graph, so we're never going to have any loops, and it's going to be structured like a tree, so we're guaranteed to not have any loops. And then space is also going to be big O of n because we do need to hold the call stack, and so worst case scenario, we have something that looks like this, right? We'd have to go all the way down. And also we do have this dictionary where we have the node and all of its children, but all of the children combined. So let me think. So node and all of its children. Yeah. So all of these lists combined will be n maximum. And then, yeah, so I think that's just going to be big O of n. It might be like big O of n plus n because you can technically have, you know, let's say you have n keys and n children, but that's still going to be big O of n. So this should just be big O of n. And yeah, so that's all for this problem. And if you like this problem, please like and subscribe, and I'll see you in the next problem of the day tomorrow. Thanks for watching.